I finally chose a title for my talk. I decided to go with one that I've used many times before, which is The Lion and the Propagation Path. I think I've given talks of this title a few times. This is a little bit of lore that comes down to me through a lineage that goes back to one professor, Howard Comfort of Haverford College, who would tell his students, from time to time you'll be asked to give public lectures well in advance, and you will know that you want to go there and you know that you want to give a talk, but you will have no idea what you want to talk about. And so at this point, if you need a title, you should call your talk The Lion in the Path, because it sounds very impressive and it's totally meaningless and commits you to nothing. Now, the organizers kindly did not request a talk or abstract from me in advance, but I wanted to go with this title to sort of note, I've been spending the past week trying to calibrate to the audience here. This is my first time at GNU RadioCon, and I noticed, over the course of the past few days, from time to time, someone in this room will say, okay, can we get a show of hands? How many ham radio operators are in the audience? And hands will go up, and they'll go, okay, that's about half. And every question that I see somebody ask that for, it's always about half. It's not the same half. So I figure anything that I talk about is going to be old hat to about 50% of you and completely new to the other 50%. And so I'm going to try and structure things so that no one is too bored and no one is too lost. But the actual point that I want to get to is building connections between the GNU Radio and HamSci communities. Phil set this up nicely with the definition of HamSci yesterday. What HamSci is it's a collection of amateur radio operators. We're basically a listserv and a set of workshops. We welcome you to join us, who use ham radio for scientific purpose. And I've stolen some slides from Josh. I'm going to put these in at a few points to talk about some ideas for how we might build connections between these communities. So I'll begin with an introduction to the ionosphere at a very basic level for those who are not familiar with it. I'm going to tell you a story about our the first big campaign that I was a part of. The first ones that happened with HamSci were the 2017 eclipse, but there was one in 2019 that I worked on for WWV. I'll talk about the first part of the personal space weather station. This was kind of the core of my dissertation work. Was the Doppler receiver we called a GRAPE. And then the WWV Scientific Modulation Working Group, which I think might have some interesting potential for collaborations. And then we'll come back to the personal space weather station as it is coming together now and the extensions that we're planning to make to that network over the next 4 years with the support we've just gotten from NSF. So slide stolen from Phil. The thing to note about the ionosphere, I've got about 4 or 5 things to kind of keep track of. The first one is that, like an onion or an ogre, it has layers. The layers are mainly the E and F layers, and then there's the D region below those. So who knows where these layer names came from? Does anyone know the story? Okay, about half. So this guy Appleton in the 60s got the Nobel Prize for ionospheric modeling, and he, I think it was him, he had a chart, and he had written E on it for voltage, because voltage began with E in the old days. And he had figured out that he was getting reflections off of this ionospheric layer, so he labeled that the E layer, and then he figured out that there was actually a second layer, so he labeled that the F layer. And then he realized there was one in between, and he was in a hurry, so he wrote in F1 and F2, and then they started calling the D region the D region. And then he was like, I don't want to change it, because what if there are A, B, and C regions, and there weren't? And we're stuck with this forever now. So yeah, so now you know. But the F layers will separate at night because of photoionization. Another thing to know about the ionosphere, besides that it has layers, is that it's very complicated and it's coupled into a lot of processes. This is an image from NASA Goddard that captures some of them. honestly, the only reason I've ever seen anybody use this image is to put it at the beginning of a geospace presentation to point out how complicated the ionosphere is, and so it is here. Okay, the other thing to know about the ionosphere is that its behavior is affected a great deal by the sun. If we want to understand the Earth-Sun system, we have to understand the sun. And the sun is a very complicated thing. If you look into the current discussions on solar cycle prediction, which are a fascinating scientific discussion of our times, and I recommend it. For those who are not thinking about this space weather all the time, it's worth knowing that there is an 11-year solar cycle. You can look in the Google search statistics and see, you know, aurora searches peak about every 11 years, things like that. How many people saw aurora during the geomagnetic storm earlier this year? Okay, about half. So this is something we can go back and we can find, you know, historically. Here's a record from the 1700s. This was an eyewitness account of red aurora in Japan. Here's one of my favorites. This is a personal theory. This is Twilight in the Wilderness by Frederick Edwin Church. And it was painted, well, it was exhibited in 1860. Does anybody know what happened in 1859? Okay, about half. The Carrington event of 1859, which was this coronal mass ejection that induced currents in telegraph lines, so that telegraphers worked out that they could send messages without a battery connected. It would be very bad if one hit us now. We came very close in 2012. But that sort of is the 100-year flood of space weather. And the curators at CMA think that he put all of these vivid colors in this painting because he was saying something important about the Civil War. I think he put them in there because he had seen aurora and it had changed his notions of what a sky could be. Plus, he drew it out in the field and then finished it in his studio in New York, so maybe he was feeling a little liberal about it, who knows. All right, and then the other thing to retain about space weather, and Phil again talked about this yesterday, is that it's expensive. It was worth $100 million to SpaceX when they launched all of their satellites directly into a geomagnetic storm in February 22. And this is a fun one because in the literature, you know, every time there is a storm, people will write papers where they'll use it as an example. And this was, I think, in one paper as the SpaceX storm before, when I would go to conferences. Like, I guess the lawyers must have descended because people then started saying things like, the February 2022 geomagnetic storm which destroyed many satellites of a company that shall remain nameless. But as Phil pointed out, this was his image from yesterday. Here's a lot of Starlink satellites currently in orbit. And if this is something that you find intriguing, I can assure you it will only get more interesting and not less in the years to come. And the final thing I want people to really remember about the ionosphere, and this is maybe the most important to this crowd, is that it's an undersampled system. This is a total electron content image, and I'm not going to talk about anything relating to this sort of measurement today, but what I want you to notice is that, you know, here's a day of data, and it's, every 10-minute cadence, and each of these pixels is like a degree latitude by a degree longitude. So what we can do as designers of instruments and open source hardware and software is build systems that can fill in some of the missing pixels on maps like this and get some better idea of what's going on. So for the purposes of this talk, we're going to use a very simplified model of the ionosphere, like at about the level when people were first thinking about it a century ago. Marconi had claimed success in getting a message across the Atlantic, and there were two different guys, Kennelly, who was a physicist working in the United States, and Oliver Heaviside, who was an engineer in England. And they both came up with this concept at the same time that, you know, the radio waves really ought to just go right out into space, you know, because the curvature of the Earth and so forth. So they must be bouncing off of something. And they both said, well, I bet that something is a layer of ionized gas. And they wrote it down and like within, you know, weeks of each other. And so that's known as the Kennelly Heaviside layer, sometimes just the Heaviside layer. How many people here are fans of the musical Cats? Okay, about half. You know where it's going. So yeah, when they say up, up, up to the heaviside layer, they're talking about the ionosphere. Fun fact. And this is also where ham radio operators come in. This on the right here is the January 1922 issue of QST, which is published by the American Radio Relay League, which the ARRL is a big ham radio organization, published to this day. And this was the first ham radio contest. The first bit of radio sport was the transatlantic test. They had stations in the United States send signals, and they were picked up by a station in Scotland. So this is a science campaign. This goes all the way back to the beginning of the hobby. And now we have, you know, radio sport, we have capture the flag, we have all of these things that have a heritage of being a gamification of what we already need to do for scientific purpose. So it makes a lot of sense for HamSci to then come in and say, all right, well, let's return to those roots and start using ham radio for science in a concerted way. You already pretty much know what ham radio is, but the thing that we like to say about it is that it's the national parks of the electromagnetic spectrum. It's certain provinces where you are permitted to go and participate in activities that support, you know, fun and recreation, international goodwill, and technical achievement. And as long as you clean up the trash and you don't, you know, have spatter off the edge of the band and, you know, don't crash anything that you shouldn't, then you're allowed to be there and you're allowed to participate in things, and there's many different ones that are worth going to try. So I want to say a word here about also what makes citizen science, because there's some definitions of this that are becoming more rigorous on the science side. On the right here, I have this article I wrote for EOS, which is the magazine of the American Geophysical Union, and it's been carried by QST in a lot of publications. My favorite thing was that they took this article and transmitted it as part of the shortwave radiogram, so I could put it in FL Digi and watch it, like, you know, print out. So that was a lot of fun. But when I wrote this, I used the word citizen science, and the editors were like, we're not sure. We want you to use crowdsourced science. Because there's a distinction drawn now between citizen science, crowdsourced science, community science. In community science, that's something where you have a population that has a concern, usually a public health concern, about something, and they're seeking out scientific aid to investigate that public health concern. So, for instance, if you're looking to get lead testing in your area, for example, and you want to do a public health study in your area, that's community science. Crowdsourced science is something like Zooniverse or something like that, where you're contributing to a training data set. And the goal is to drive things through this progression to what's called co-designed science. So real citizen science should be something where the volunteers are part of the process at, you know, about the same level as the folks who are coming in with real training and background. The volunteers should be active participants to the point of working on the hypotheses and the formulation of experiments. And that's the direction that these things are going, and everybody should be given credit for their work as well. That's also very important, because you don't want something where people are just asking for someone to go in and count things and working for free and not actually understanding what they're working on. That's not really participatory. And this is something where, you know, amateur radio, I think, is very well positioned to build towards this. You have to scaffold toward it to make sure that there's resources explaining what you do. We already kind of have that. Little shout out to my home club, the Case Amateur Radio Club at Case Western Reserve, W8EDU. Our first paper about amateur radio was this paper in 2017. We taught a writing class with it. So for the educators in the room, if you are looking at different classes, you know, don't just limit yourself to DSP, right? We used this as a way to talk about constrained communication, communication at a distance, censorship, you know, technical education. There's lots of interesting angles to be taken. And what we found in putting this together was that this was a way for us to become legible to the university. If you have a college radio club, and I won't belabor this point too much for the folks who aren't dealing with this sort of thing right now, but it's hard to maintain roof access. And it's hard to, get the university to understand the resource that it represents. But if you can integrate it, as we have done, into curriculum and research and recreation, extracurricular stuff, then it becomes much clearer what it's about, and it also helps push things in interesting directions. We have used the Ham Radio Club at Case as a curricular lab for 8 different courses, many of which are core to the electrical engineering curriculum. So happy to talk about that if anybody wants to. And so this put us in the position to host HamSci 2019, which was where a lot of the ideas that I'm going to show you here came together about WWV. There's Phil with our faculty advisor, David Kasdan, 88Y. And, this is where I think one of the GNU Radio strategic plan aspects comes in, which is this concept of spreading it to increase the footprint in educational programs. I want to encourage folks to think about ways that you can extend GNU Radio into the amateur radio community and vice versa, whether that be getting your license if you haven't yet, or maybe if anybody wants to set up a table at Hamvention with us at the HamSci Collegiate Amateur Radio Initiative booth, things like that. Youth on the Air. There's a lot of ways to make the ham radio community aware of GNU Radio as a resource that they can use and contribute to. So in the interest of building up to these, the system I'm going to talk about, we had several campaigns. I'm going to talk about the first one, the Festival of Frequency Measurement. Most of these were around eclipses. But this one's kind of a fun story. So first, let's talk a little bit about WWV. How many people know what WWV is? Oh, good. That actually might be more than half. Yeah, this is the heartbeat of the ham radio spectrum. You turn to 10.00000 megahertz, and you will hear, at the tone, the time will be. WWV, all the time, all the time. So there's WWVB, which is the transmitter that runs your atomic clock, if you have a radio-controlled clock at home. There's also WWVH, which is the sister station in Kauai. It has the same carrier frequency and similar sideband modulations, but it's a little bit different. So time standards in general. There's 2 basic questions for a time standard, right? You have how do you measure the time, and how do you disseminate that measurement? So here's some fun ways of, we've got some sundials here. You've got a courting candle, so if somebody is coming to visit, you can adjust how long it will take the candle to burn down based on how long you want them to be there. This is one of my favorites. This is a meridian cannon. It focuses the light on this wick, and then the cannon goes off at noon. So it's safe to operate in Cleveland. There's no sun. And then disseminating measurements. So we're now at the point where we have these radio-controlled clocks, and then it's a different system, but this is the Primex clock in my old living room during daylight saving. It can only go forward, so to fall back, it has to go around 11 times. Okay. So really what this is all about is I really want to tell you guys about the Dombey Affair of 1793. But we're going to go back to the forming of the United States and how NIST came about from this. So 1788, we ratified the Constitution. It has Article 8. Article 8 says we need to have a Department of Commerce, and that Department of Commerce is going to be responsible for, among other things, weight and measures. And this makes a lot of sense, as a thing for a nation to do, because the first time that any 2 cultures meet, they're either going to do it in commerce or they're going to do it in war. And there was a dichotomy of views among the colonies about things like how big a bushel was. So you could make, good money doing arbitrage between 2 different adjacent states that had different opinions about how much a bushel should be. And Jefferson was somebody who was very interested in standardizing this. So in 1790, he wrote the Jefferson Report, and he had the first American standard for time, which was this pendulum simulation that you see up in the upper right, where you have a particular length of rod, and you check to see the period of that as a pendulum, and you say, okay, well, that's about a second. The issue, of course, is that in order to do that, you need to have a standard for length. So around that time, he writes his friend Joseph Dombey in France, and he says, hey, can you come to the United States, and can you bring me a kilogram and a meter stick that are in line with the French standard so that we can standardize about it? And Dombey says, sure, yeah, the French Revolution is happening, and I'd rather not be here for that in person. So better? Thank you. So he gets on a boat and he brings yeah, we'll just do this. He brings the kilogram and the meter stick, and on the way, the boat is captured by pirates. It was a very sad story, actually. Dombey died in prison. But the pirates took the kilogram and they took the meter stick. And that is how close we came to being a metric nation. It might be the most expensive thing that has ever happened. Anyway, so after that, it took us like a while to get it together. So it wasn't until 1838 that Congress actually officially adopted a common system of weight and measure. And then it wasn't until 1900 that they found the Bureau of Standards, which today is known as NIST. So, okay, let's get to the part where radio comes in. So one of the first things they did, 1919, is the point when they announced award the call sign for WWV, the standard station for the United States used to disseminate time. And they were, putting various signals on this. I just love this quote. This is a snippet from an internal newsletter. This was when WWV was in Gaithersburg, or not Gaithersburg, in DC. It was actually in the building that is the visitor center for NASA Goddard now. And essentially what they're saying here is like, oh, we figured out that you could put music on this, and then you could listen to music, but far away from the music. And it was nice. A fellow could have a nice evening that way. So really early days of radio here. And this was, I think, the first clockwork setup here, and they've improved over the years. I had an opportunity last year to see the clock in Boulder, the cesium fountain that is the time standard, and also to see the strontium system that they're going to transition to. And that line will keep going. We're down to 1 part in 10 to the 18th, which is very exciting. So, okay, here's the part of this where the story gets kind of fun for me. 2018, there was a proposal to defund WWV and WWVH. And this was something where within the ham radio community, people picked up on this. And I remember the HamSci mailing list, there was a discussion where 3 or 4 people came in, they were like, wow, I'm using this for 7 different things, but I can't really think of a good reason to keep it. So I guess it's just going to disappear. And I wrote a blog post on our website with, here's who you should call in Congress and annoy, and here's what you should say in order to annoy them. And this got picked up in some kind of surprising places. It showed up in a bunch of blogs. It showed up in other ham radio magazines and websites. I don't think that we were what tipped the scale by any means. I think this was like many things in radio. The Navy needed it for something, and I'll never know what it was. But in any event, they did end up keeping it, and because we had been part of this whole effort and been in touch with people, we got to go to the party. And this was the centennial party that was held on actually the day they would have defunded it, which was also the 100th anniversary of the awarding of that call sign. And so we had a ham radio contest. And brought all these people together and sent out special certificates. And one of our goals was to use this as a way to justify WWV as a scientific resource. So we ran this campaign called the Festival of Frequency Measurement, where people would measure the Doppler shift of the carrier. And you can see, here's some stations on the west side of the country and some on the east side of the country, and they're seeing regionally similar pictures. And so this was a good and promising result of this distributed method. Now, the reason we were able to do this is because of a contest that already exists called the Frequency Measuring Test, which is just what it says on the tin. And this motivated somebody to put this into FLDigi so that you can go into the waterfall and you can click a carrier, and it will estimate where that carrier is over time, and then it spits out this nice CSV file. And this was the foundation of our research for like 5 years, was this this aspect of this piece of software. Another slide stolen from Phil here. I want to direct your attention to Bright and Tuva, who are the 2 dudes on the left side. And figure 9 at the top here, this is from their Nature paper in 1926. Note the radio station that they're using. That paper is entitled On the Existence of the Conducting Layer, I think, something like that. It's very early on in ionospheric physics. So we're really doing the same types of measurements that they were doing. Okay, so what do we got that they ain't got? And the answer is Raspberry Pis, GPS-disciplined oscillators, the internet, open source software, the ability to take many different stations and use them all as one coherent meta instrument that's all looking at the same thing. So really what has changed most of all, apart from, some of the technical details are a little different, but what really is new is the idea of cooperation. A little bit about the frequency measuring test. So simplified model of Doppler shift. This is all models are wrong, but some are useful time. So the sun rises, photoionization occurs, what we call the virtual height of the ionosphere. So if we imagine it as just a mirror, and it isn't, but if we imagine it as just a simple reflecting layer like Heaviside might have thought of it, then that goes down during the day, right? And those wavelengths, the wave fronts of our signal, which is at leaving WWV on the left at 10.0000000 megahertz, those wavefronts get scrunched and it arrives at our receiver at W880U as a slightly higher frequency while that change is happening. Evening comes, the process reverses, the wavefronts get stretched further apart as the virtual height rises. You end up with something that looks like this. So you have a pretty typical shape here where there's a sunrise peak in the middle of the day, and then you can kind of capture traveling ionospheric disturbances, which are these waves that go through the bottom side of the ionosphere. And when you have enough stations, you can start to build something of a picture of them. So it's a blind men and the elephant situation where we are looking at different aspects of the, looking at the situation from different angles. You can't get all of this information from one station. You have to have multiple ones. And the more you have, the better. And the greater density you have, the better. And so this is a wonderful thing for ham radio operators to do because there's utility to having many stations out there. Okay, so the first part of the low-cost personal space weather station is, this is our system here. If you're curious, there's a link in the top right. That DOI will take you to the paper that describes all of it. So I won't go into too much detail about the hardware. In fact, I'm just going to skip through all of this. All you need to know is that it's a low IF receiver. And we call it the Grape because it's easier to say than low-cost personal space weather station because people like to name electronics after tiny fruit. You got your Lime SDR, your Kiwi SDR, you get the idea. And it does its best work in bunches. And the other thing that people insisted I add was that we hope the data will ferment into something quite nice. And I gotta tell you, it has. After going through 5 years of cataloging Doppler flashes from solar flares that we never expected to see in the data. So at the time that I put this together, we've got over 100 stations. Support for this is provided entirely by volunteers. The volunteers do absolutely participate in the engineering side of it. Here's a 3D printed case for it that some guy just made. We use it now. It's great. Here's what we had from yesterday. This is a little bit active because we're in a very active period right now. We just coming out of a G4 storm, I believe. If you look at, this is 24 hours of data. Each of these lines is put together as one of the stations in the New England grape cluster. I think there might be one outlier in British Columbia. And these plots appear in my email inbox every night at 9 o'clock. They are prepared by a group of ham radio operators, and it's my favorite thing. And I look at them and I look for the solar flares, and that's what I do instead of Wordle. So what's happening here is, one of the most interesting parts to me. At about 15:30, you see how there's all of those stations, there's a peak with all of them lined up. Pretty sure that was a solar flare. So I will take a look at that, and then I take a look at space weather and confirm there. So we got an NSF grant to measure the 2023 and 2024 solar eclipses with these and to install a bunch of them in order to do so. And the thing about an eclipse is, we talked about the relationship of photoionization. An eclipse is it's the closest you come to getting a controlled experiment in space. You have this known bit of darkness, and it lends itself very well to a campaign. The history of eclipse science is a very interesting one. For us, it was an excuse to put together a lot of stations. These are the volunteers who did that. Bill Blackwell in the second photo is the one who puts together those plots. And these guys built the more advanced version of the Grape, which is listening for audio and captures the sidebands as well as the carrier. This is still a narrowband receiver. We'll come back to that. Here's another couple plots from the New England Grape group about the eclipses. We've been chasing these S-curves for many years. This was the annular eclipse in October. Here was the eclipse in April. I didn't even bother boxing it because it's obvious, I think, where it is between 1800 and 20. So it's the night-day cycle in miniature. And you can see that it sort of, if we had mapped these by longitude, you could see very easily where it sort of has slid across the country. So it was nice to get that, and we had a nice quiet day in space weather that day. Because we have many stations, we can look at events coming from above and below the ionosphere. This is the wonderful thing about it, is that it has all of that coupling. And so you can, it picks up on these things. And so we have on the left, there's a couple instances of solar flares. There's an X1 class solar flare and a C4.9 class. There are some advantages this has over super darn radars. We have a 1-second cadence, which is very nice. And the spatial distribution, the low cost, etc. And then on the right, this was from the Tonga eruption in January of 2022. And you can see the Lam wave, which went all the way around the planet, showed up in our data as well. Data collection process, basically we put it on an FTP server. Again, there's a paper describing all this. Here's example data from one station. This is our pilot node. And the plots on the right are each of those lines of pixels from 0 to 24 hours. That's one day, right? And it's color mapped. The top one's according to red-blue for Doppler shift. And so you can see the change in length of day over the course of a couple of years that way, and you can look at long-term variability. For those anybody who might be colorblind, here's an alternative color map for those images. The part where in the lower plot, which is power, what's happening there at that line is that he swapped out his antenna for a less noisy one, so everything becomes a little bit clearer, and it's nice to be able to see those sorts of things. All right, so at this point we've got these receivers. They're narrow band. They're almost all looking just at the carrier, really. So what else can we get out of our time standard stations? WWV is a fantastic resource because we don't have to maintain it. It's very loud. It's got this very precise carrier. But there's other things that we want to explore because, again, our model is not really accurate to everything that's going on. We usually will have multipath. We have refraction in the ionosphere. It's a more complicated story than just the carrier would lead you to believe. And there are these different elements of the modulation that can be used for different things. You've got the carrier signal that we've been using, but you can also look at the second ticks. Time of flight is a fantastic thing to know if you're trying to actually build a model of things. The carrier is actually not a great, observable. So we were looking at some of the different ways that we could use these. And we were also in conversation with folks at NIST about what we might add to make it more useful for scientific purpose. So for a couple of years now, I've been running the NIST Scientific Modulation Working Group for WWV and WWVH, and this is our signal that plays at 8 minutes past the hour. I don't know if there's a way to turn this up. Perhaps not. Well, you can see it in the spectrum anyway. That's the voice announcement. Pseudo-random code. Here's the phase coherent tones. This is for testing the linearity of the transmitters. Chirps. I always like that part. And then we have just a single impulse, and then the same pseudo-random code again, so that you can compare them. So I think that this, going back to, how does this fit into the priorities for GNU Radio, we have a number of projects, this is one of them, where I think GNU Radio can be very helpful for analyzing some of these things. Most of what we do, we just shelve our data. We don't have real-time stuff. And we'd like to get more real-time stuff, and we'd like for that software to be, durable and manageable. We can certainly use help with that. Another thing that I think is worth pursuing is using these time standard stations as test signals. They're very accessible. I think that anything that that make sure that they're useful and can demonstrate that they're useful is a good thing for keeping them around. And you can incorporate them into educational activities, have people go and measure one of these signals, and then integrate that into whatever flow graph you might be working on that day. There's many aspects of the modulation as shown that can be used for different things. So there's a couple of DOIs on here to access the code that's used to generate that signal and things like that. And then we have, analysis of eclipse data. The GRAPE2, as it was called, that one that I showed all of them lined up that measures the sidebands, that collects everything in digital RF format as well. So we will be working on a workflow for analysis that will hopefully be compatible as time goes on. All right, so now we get into the next steps for the PSWS, and here's where we finally get to some proper SDRs. I've stolen these slides from Nathaniel, so hopefully I can do them reasonable justice. So at this point in the story, right, we have these passive receivers, and they're narrow band, and we can do some things to give them some more stuff to look at, but we're still only looking at 2.5, 5, 10, 15 megahertz. We're not getting the full picture. And what we'd really like is something that's like, more like a Kiwi SDR, but more scientifically usable. Essentially what we would like is a USRP, but cheaper. And so this was the goal that we set out with the original vision for the personal space weather station. So initially we worked with Tapper on putting together what they called the Tangerine SDR. It's been a valiant effort, but they were not able to keep pace with turnover of FPGAs. So while that was going on, our friend Phil Karn of KA9Q Radio, developed his software further, and we worked out that that was capable of doing pretty much the things that we needed it to do, of creating these arbitrary slices so that you could have virtual receivers from the raw IQ data. And the RX888 turns out to be at about the, there we go, yes, thank you. Please direct your attention. Yeah. The RX888 turns out to be the right size and price and capabilities for a lot of what we want to do. So this has been prototyped, and I'm going to show you a couple of examples. Rob Robinette AI6VN has been a lead on this part of the project, and here's some of the things that we wanted to accomplish with it. Basically to have something that fits into the network we currently have while also really increasing its capacities. The other nice thing about this too is, we started collecting in 2019, right? And the network has continued to grow pretty much organically of the GRAPE receivers. The interesting thing about that is that a solar cycle is about 11 years, and it would be really great to get, data that spans a solar cycle or two, so that we can get good points of comparison that way. So we don't want anything that, diminishes our legacy data, as you might call it. We want something that fits in with it where we can integrate the analysis. And one nice thing about this that I really appreciate is that, especially for that solar flare study that I mentioned, we can go in and generate GRAPE-like data from it. Let's see. So then the other thing about it, using Whisper Daemon, at this point, when we've added these SDRs in, it is it's still a passive network, right? We now have our narrowband piece and our wideband piece. And we can get a lot of information out of looking at Whisper and out of looking at sort of the aggregate of existing ham radio contacts. One of the things that happened in 2017 was there was a contest for the Eclipse, and Nathaniel and some other members of HamSci did the statistics on reverse beacon network and PSK reporter and other things where people, collect records of ham radio transmissions, and every time you have a record of a ham radio transmission from point A to point B, it means that there was a path there. So if you look at this over the course of a day and you have these, millions and millions of records, you can start to build a little bit of a picture from that, just from people going about their business as ham radio operators who want to talk to each other and see how far their reach of their station is. So this would fit very neatly into that system as well, and then we can continue to use that part of our analysis pipeline. And so here's what a complete receive station looks like. I'm going to show you a couple of examples for Nathaniel Station, which is in Scranton, Pennsylvania. Here's the annular eclipse in October 2023. So I showed you that line graph with all of those lines from the Grape Run receivers. And so this is a much more interesting thing, right? To be able to see the proper spectrum, you get a lot more data. But then you also have all of the frequencies in one place. And you have WWV, you also have the Canadian standard station CHU. So in these, there's some dotted lines, right? The one that is sort of the longer dotted line coming up from the bottom of the plot, that's the measure of solar zenith angle. And then the one that is like a V that's superimposed over that, that's the solar eclipse. So you can see how the different frequencies responded differently. And then we also have the CHU data. So compared to that little line, it's like this whole network is putting its glasses on. We're going to be able to see so much more for any given station using this hardware. And then to top it off, we also have VLF receivers. This is an example of a plot. This is just looking at man-made signals, but they can also pick up whistlers and interesting, natural VLF signals as well. And then we can get more data about our traveling ionospheric disturbances and things that we're curious about. And I don't know yet everything that we'll be using the data for, which is very exciting. I think that once people can get a chance to actually, look through their microscope, then they'll come up with ideas for more things to look at. But at this point, we still want to get in some sort of active component. Phil addressed yesterday the concept of having the combinatorial number of propagation paths. How many transmitters do you have? How many receivers do you have? You do a lot better if you can add in some transmitters. And so enter the WSPR sonde, developed by Paul Elliott, WB6CXC. And this is documented at the Turn Island Systems page. Here's some examples of it in action, where we have a couple of different stations that are looking at the WSPR transmissions. Gwyn Griffiths has done a bunch of work on this, and I recommend the presentation that's linked at the bottom. All of the HamSci stuff just got posted to YouTube in 2024. I'm going to skip some of these for time because I'm running a little bit short. So as of May, here's what this looks like. We've got some WSPR sonde transceivers that have been deployed. And we also have the HamSci ground magnetometer. The goal of the personal space weather station is to have it be just like a weather station, something that's modular, where you have a central computer and then you can add in other types of instrumentation later. Not every weather station needs a rain gauge and a barometer and an anemometer, but you can add those in and take them out and have things drop in and out of the network as needed. We're trying to do something very similar here. And so that'll include magnetometers. I'm hoping for all sky cameras in the future to be something that we integrate. And all of this is going to come together at psws.hamsci.org, so watch this space. So yeah, at the time of writing, we currently have this system that we've determined works for our purposes, and we are going to be installing some WSPR sondes. This one might be a little bit of an eye chart in the room here, but what I have here is a table from the grant that was just approved by NSF to deploy additional stations and support the ongoing development of the personal space weather station. So we're going to be deploying 30 VLF receivers across the country. We're going to be deploying 30 ground magnetometers, 30 of these RX888 receivers, and 10 WSPR sonde transmitters. So the network will now become an active network. And this also means that we'll be able to come up with our own modulations and transmit them and put together science campaigns. And this, I think, is where perhaps GNU Radio could come in, because in the sustain portion, there was talk of how do we build more partnerships. There was discussion of how do we do small grants and small projects, the kind of thing that might be the size of a senior project or a master's thesis is the sort of thing you could drive with GNU Radio. And so that's, I think an area that would be worth exploring further, especially for both the purposes of things that occur as campaigns and experiments, but then also extending the analysis pipeline. So I know that there's work in integrating Whisper Demon and K9Q Radio. Please continue to do that. And I'm not well versed in that part of it yet, but I think that it's a wonderful thing that all of these different environments can come together. So with that, I'll acknowledge the NSF for these things. Thank you very much to GNU Radio and to the SETI Institute for making it possible for me to come here and speak to you today. I'll ask that everybody save the date for HamSci 2025, which is going to be at the New Jersey Institute of Technology, March 14th through 15th. We hope to see you there. It should be a wonderful time. For those who are curious about the Personal Space Weather Station, or at least the GRAPE part of it, this is a summary of the publications describing it, so happy to share this for anybody who is curious to hear more. And I'll leave it on this slide for how to get involved with HamSci. And I hope that if you are considering getting your ham radio license, that this has perhaps given you a little more reason to do so. So thank you very much, and 7-3.
Where does one get a grape from?
Oh, yes. Okay, so you can go to the HamSci website. If you go to hamsci.org/grape, right? And it'll take you to a paper that we wrote. There's this fantastic journal called Hardware X, and I'll mention for the folks in the room, there's also one called Software X, where you can put together documentation of your hardware, and it's like a slightly more rigorous version of like an instructables page almost, right? And that is maybe the most useful paper I have ever published, because if anybody has questions about the GRAPE, I can just point them to that. So of those 100 stations, many of those people have completely built it on their own recognizance. If you choose to build one, the Bodnar is like $100, I think, to get the mini Bodnar that we use. That's the GPS disciplined oscillator. The board itself is available from OshPark. And then it's a very simple soldering project. It's about, student level. The only tricky part is that the mixer chip is becoming unobtainium, so you might have to contact somebody in HamSci and they'll mail you one. But yeah, you can put one together, and it's I think it's a great introductory project, and it's been very good for high school level, things like that.